page from yesterday, so you don't have to write that down, but then the rest of the notes you're going to write down, so you want to have some paper out too, but I just kind of copied this slide over. There's going to be a lot of theorems that are thrown at us in calculus. And every now and again, maybe more often than you would think, on some free response questions, they want you to use those theorems. They want you to justify your answers based on those theorems. And 45 and 51 are examples of where you can use the intermediate value theorem. We're like shortcuts here, shorthand here. So intermediate value theorem, IVT, that's the same as intermediate value theorem. And if you read it, it says a function that is continuous on a closed interval, a to b, will take on every value between f of a and f of b. Those are y values, yes? So this is saying for every x value on a closed interval, that function has to take on every y value also in those intervals. In other words, here's a lovely little picture here. If this function is continuous between a and b, one, if it's continuous, by definition, do you agree that every x value between a and b has to be used? All the intermediate value theorem says that if it's continuous, there also has to be a whole set of continuous y values. So if every x value between a and b has to be used, does it make sense that every y value between whatever the first y value is and the second y value is also has to be used? That's all that's saying, but it's kind of important. And if you look back at 45 and 51, they're asking you questions that can be answered by the intermediate value theorem. If it's a continuous function, then I know this has to be true. If it's continuous, and I can see that it crosses the x-axis one time, then I know there's at least one zero because it has to take on every value along that line. So that's the idea of it. We're going to come back. Maybe we'll talk about 45 and 51 a little bit more tomorrow. But that's all that's saying. All these y values are being used in the same way that all these x values are being used. Yes? It's not terrible, right? Only works if it's continuous. That's why continuous is so important. If that's not a continuous function, we don't know if all the y values are used because it could skip over it. It could have a hole. It could have a jump. It could have an asymptote. And there might not be some y values used. But if it's continuous, all those y values will be used over the same interval of the x values. All right. We're going to kind of go back to that average rate of change, instantaneous rate of change stuff. I believe the first day we started this chapter, we started with the idea of what is your average rate of change. Outside of class, outside of math class, you might say, what is your average speed? Or what is your average velocity? Meaning, on average, how fast were you going? Well, that's really just saying your rate of change. And remember, we talked about on that first day, if you want to find your average speed, you take your total distance divided by your total time. Well, we can do that with anything. So your average rate of change, you're going to take the amount of change, so the total change that happened, and you're going to divide by the length of the interval. So just throwing that out here, just forgetting about talking about speed, just thinking about a line, using this first sentence here. If I have the interval from A to B, that's my x-axis. If I want to find the average rate of change, I'm going to take the y values that go with that. So I'm going to take f of b minus f of a. Remember we talked about average rate of changes like slope over the total length of the interval, which would be b minus a. If you go back and look to day one, when we did that, that's exactly what we did. Only we were talking about like feet and seconds instead of talking about an interval. And we're going to going to talk about this sentence in just a minute, a little bit more, but the average rate of change can also be thought of as the slope of a secant line to a curve. And that's because if you have an interval, you have 2 points. And if you want to find the change in 2 points, that's slope. You just take the y's minus the x's. But for a secant line, you have to have 2 points. That's why it's the average rate of change, because you're taking the average between those 2 points. So I was telling Caitlin this morning, because she was worried, she looked through the section last night because she knew she wasn't going to be here, and she said it looks really hard. But I told her it's actually really similar to what we did on that first day, going back to the average speed and the instantaneous speed. It's just talking about it in terms of functions now instead of in terms of speed. Does she already have notes? No, but she's coming back later. She's going to be in 6th hour, and she's going to watch these notes in 6 hours, I think, and annoy everyone else in 6th hour. So, find the average rate of change of this function over the interval from -2 to 4. All I'm going to do is find the average rate of change, or the slope of the line that would go from -2 to 4. Remember, this is not an ordered pair. This is your x-axis interval. This is like saying from -2 to 4, how much did my graph change over time? Or average, how much did it change? And I'm just going to plug it in up here. My y values subtracted over my x values. So I'm going to take f of 4 minus f of -2. That's the change, the amount of change from one value to the next, over how long was my interval. And the easiest way to do that is just to subtract the 2. Or maybe you could just say, how long is it from, if I go from -2 to 4, it's really just 6, right? But I could just write it as 4 minus -2. I like to think about it as slope, rate of change. And you should just get a number value out of this, just like we did day 1 with this chapter. Average speed or average rate of change, you should be able to tell me a number answer here. Remember that this means I'm plugging in up here, so I actually have to do a little bit of work. So I'm going to get 2 times 4 squared minus 3 times 4 plus 7. Be really careful because you're subtracting, so I'm going to put a parenthesis there. Subtracting all of f of -2. We get 2 times -2 squared minus 3 times -2 plus 7, all over 6. There's definitely a lot of room for arithmetic errors on this. I would highly recommend showing me a little bit of work, because if you just do it all in your calculator or do it in your head and you get it wrong and I can't see what you did wrong, I can't really give you partial credit. So show a little bit of work. You don't show everything, but anyone have a question on where I'm getting these numbers or values? So 16 times 2, I think that's going to be 32, minus 12, plus 7. 4 times 2 is 8, but that's going to be minus 8. 6, but it's minus 6. Minus 7. Right, if that's the only step you show me, that's much better than just giving me straight an answer. Again, notice I distributed my negative because that's a big mistake that people make. Yeah, you can, like, do all that and then subtract or whatever. Yes, as long as you're doing the arithmetic correctly. I got 6 over 6 or 1. Did you get that? Which means if we graph this, I don't really want to graph this one, but if we graph this, this would be a parabola. Do you agree with that? And I could even say it's a parabola opening up. I don't really know a lot about it, but I'm just going to make a little graph here, and I'm just going to say, I don't know, let's just say it looks something like this. That's totally not what it looks like, but let's just pretend for a minute. If I looked at the value at x equals negative 2, which let's just say is right here, x equals negative 2, and then x equals 4, let's say that's right here. If I connected those and made a line, what I've just found, the average rate of change, I've just found the slope of the line that goes through those 2 points. That works for any equation. Up until this point, we've only been able to find the slope of linear equations. We've never talked about the slope of a curve at a point. Well, this is what we're doing. When we're finding the average rate of change, we're finding the slope of the line that would go through there. Okay? So, how does this all connect to calculus? Let's see. What I really care about is the instantaneous rate of change, which means at a specific point, what would the slope be, or what would the rate of change be? Which means instead of talking about a secant line, I want to talk about a tangent line to a curve. So in a circle, way back in geometry, I'm sure you all remember this like it was yesterday, but in a circle, a tangent line is a line that's perpendicular to the radius of a circle, which means that it just kind of like touches the edge of the circle. In other curves, a tangent line can just be any line that just touches it in one point. And we kind of talked about this when we first started this, and you're probably like, I don't know anything what you're talking about. And I tried to define what a limit was, talking about secant lines. But what we're going to do is we're going to use a secant line, and actually we're going to use a secant line and the concept of limits to find our tangent line. So let's see if I can try not to, okay, I need to like double, can I like double page this? How do I do that? Dang it. Humor me for a minute and don't write this part down. Draw a little graph. Look, now it comes up. It was just delayed. Because I don't want, like, when you see something on the board, many people just hurriedly write it down and ignore what I'm saying. I'm not just up here rambling for no reason. Like, what I say is important sometimes.
So that example that we just did isn't going to be like anything on our homework?
It is. It's going to be on your homework. It's going to say find the average rate of change. And I can guarantee on the AP test, there are going to be problems that you just find the average rate of change using slope. Every year. Free response, there's at least one part of a question that you have to be able to find the average rate of change. But the majority of what we're going towards is we want to find that instantaneous. We don't want to just know over an interval what's happening. We want to know at specifically x equals 3 what's happening. And so that's the other part of it. But the average rate of change is important also. I promise. It's not going away. All right, so let's draw a little graph here. I'm just going to draw a little curve, like from here to here. And I'm going to call this A on my x-axis. And I'm going to pick another point up here. And I want that, think about what we talked about with limits. I want that to be a little bit more than A. We did that with a table by doing like 1.1, 1.01, 1.001. But to show it algebraically, we want to say we want to add a little bit to A. We're going to say A plus H. Which means, do you agree if I wrote the ordered pair for this point A, this would be the point A, f of A? Everyone okay with that notation? And so this one, not as pretty, but this would be the point A plus H, comma, f of A plus H. And what I really want to do is I want to know what's happening at A. What is the rate of change, not the average rate of change, what is happening at A. But I can't do the rate of change formula if I only have 1 point. So this is where the 2 points come into play. If I connected these 2 points, do you agree that this is now a secant line? Yes. What I really want is the tangent line. And the tangent line would just touch here at A. Don't you wish you had different colors? This is where the idea of a limit comes into play. What would happen if I kept picking, what if H kept getting smaller and smaller and smaller? What would happen to my secant line? It would get closer and closer to the tangent line, and I don't really want you to draw this on your paper because it's going to get ridiculously messy. But instead of picking H over here, what if H was half of that and it was right here? Would that now make a secant line that was a little bit closer to my tangent line? And what if H got even smaller than that, like all the way right next to that? That would technically still be a secant line, but if I connected those 2 points, would that be really, really close to my tangent line? What value of H would get me my tangent line? 0. And that's where the idea of a limit comes in. If H is getting closer and closer to 0, I'm going to get closer and closer to my actual tangent line. So we can say that the limit as H approaches 0 is actually going to give me my slope of the tangent line, and I'm going to give you a lovely little formula for this. So I used M here, meaning slope. Slope, average rate of change. Those mean exactly the same thing. To find the slope of my secant line using my 2 points, we're still going to talk about the change in y values over the change in x values. But now I'm going to use my a and my a plus h. So my y values are going to be f of a plus h minus my other y value down here, which is f of a, and if I subtract my x values, this x value from this x value, I'm going to get a plus h minus a. That should be vaguely familiar to you when we talked about instantaneous rate of change, because that's exactly what we were doing with the instantaneous rate of change. We just didn't talk about being a tangent line very much. So every time, it will just be h on the bottom. Do you agree with that? So here's our big formula for the day. The slope of a curve at any specific point. So not just comparing 2 points and finding the average value. If you just want the slope at one specific point, and they're calling it a f of a, just like I did, that slope is found by finding the limit as h is going to 0 of that exact slope formula we just wrote out. So when it says find the slope of the curve, it means do this. It's not just going to say find the instantaneous rate of change. It could. But today the key word is finding the slope of a curve at a specific point. I wish we had like a period and a half. No, I need more time. Why can't this just be it? Well, we haven't even done the example. Are we learning more today? No, but we need to do some examples of this, right? Can I go? Okay, so before we do an example, I got to give you all the stuff that means the same thing, because the big thing when we take the AP test, and you're going to see when we start practicing the AP test, they're not going to write it the same way every time. Your book's not going to write it the same way. My tests aren't going to say it the same way. So you got to know that there's many ways to say the exact same thing in calculus. So all of these mean the same thing. And so if it says do this, it means use that limit formula that I just gave you. So we just talked about this. If it says the slope of a function at a specific value, that's what we just defined. If it just says find the slope of the tangent or find the slope of the tangent line, remember, tangent line only touches it in one point, so that's another way of asking you to do that problem. And going back to day one, it could also just ask you to find the instantaneous rate of change at a specific point, which also means find the limit as h is approaching 0 of those values. We're always doing h go to 0. You know what I'm saying? Like, it's always going to be a and a plus h. And then the last way is they could just say, find this, which is exactly the formula that you're going to be using. On a test, I'm not going to be able to help you on the vocabulary part because I'm trying to get you ready for the AP part, which means on a test, if you come up and say, hey, does this mean do the limit thing? I'm going to say, I can't tell you. You're supposed to know that. So you need to make sure that you know those things all mean the same thing. All right? Now we can do an example. This is an exciting day. This is almost as exciting when we learn how to do a derivative.
Do what?
A derivative. Because this is like what the whole first semester of calculus is built around, the slope of a tangent line. Like for the rest of the year, every day we're going to be talking about the slope of a tangent line at a point on a curve. You good? No point in doing a review chapter because then still people forget how to do algebra later on, so I decided to sum up the review chapter and then we'll hit the review stuff as if we Alright, find the slope of the curve at x equals a for y equals 9 minus x squared. So we're just starting at this one. They're not even giving us an a value. We're just going to leave it as a as we go. So if I'm using x equals a, do you agree that that's a, f of a is my point? Yes? Here's my formula, or here's my equation. This is my curve. I want to know at any a value, what could I do to find the slope? And I'm just going to start with my formula. I'm going to take the limit as h approaches 0. This is the formula you need to know. F of a plus h minus f of a. And you can subtract the x values if you want, but every time Sarah pointed out, it's just going to be h on the bottom. So you don't have to write a plus h minus a, but it's okay if you do. So here's a nice little review about function notation. If I'm doing f of a plus h, when I go up here, I have to replace x with a plus h. Do you agree with that? So I'm going to get 9 minus a plus h squared. That would be f of a plus h. Everyone with me on that? Minus f of a. And again, remember you're subtracting this whole thing. So you can either distribute as you go, or you can put a parenthesis here. If I just plug a up here, what would I get? 9 minus a squared. It's been a while since we did this back in section 2.1. But here's the problem with the limit. Can I just plug 0 in for h right now? Because I can't get 0 on the bottom. Every single time, you should be able to simplify the top so that you could factor in h out and cancel it out. If that doesn't happen, you've either done something wrong or it doesn't have a limit. But I can tell you, more often than not, you should be able to work it out. So if it doesn't work out, go back and check your multiplication. So here we go. The limit as h approaches 0. All right, how about this for some good math? I'm going to FOIL this out, but distribute the negative at the same time, right? So this is going to be a squared. That's going to be minus a squared. The middle is going to be 2ah, but it's going to be minus 2ah. H squared, but it's going to be minus h squared. This one's easy. Minus 9 plus a squared. You should see everything without an h should cancel. If it doesn't, go back and check your negatives, go back and check your multiplication. But I have a positive 9 and a negative 9 are going to cancel out. A negative a squared and a positive a squared are going to cancel out. And so what's left? Could I factor an h out of that? The nice thing is we know what should happen. So it kind of helps you. Sometimes I do this and I don't get it to cancel out. And I'm like, man, that should have been a negative. So I go up and I check my work there. So I'm going to go ahead and factor an h out of this. And I'd be left with negative 2a minus h. You might say, why wouldn't you factor a negative h out? You could, but all I'm trying to do is get that h to cancel out so I can do substitution for my limit value. So that's why that's all I cancel out. That's all I factor out. Everyone with me to here? So I could cancel these out, and then can I just plug 0 in for h? And would I just get negative 2a? Since they didn't actually give me an a value, what I ended up with is actually an equation that would work for any point on the graph. If I said find the slope at a equals 7, could you plug that in here and tell me what the slope is at a equals 7? Yeah, it'd be 7 times negative 2, it would be negative 14. So if they give you an x value or an a value, you can plug it in from the beginning or you can wait and plug it in at the end. But every time you should get that h to cancel out. Michaela, do you have a question? Totally had another example, but I don't think we're going to make it because it's prime time. I'm not going to be here tomorrow because Parker really does have a doctor's appointment tomorrow. 100% sure that he has a doctor's appointment. So I will be here after lunch. I have a worksheet for you tomorrow. I'll probably go ahead and do the next example that I had just because I know it will help you on the homework and on the worksheet. So it'll probably be like a 5 to 10 minute video that I leave for you tomorrow, and then you'll have a worksheet. And then Thursday, we'll go over the questions that you had from the homework and from the worksheet, and probably do some more notes on it.
Okay, so those are the types of answers we'll be getting.
Well, you might be getting a number. Like, I really wish we had time to do one more problem. Like, if it said x equals 2 here, could you do the exact same thing to this problem, but instead of putting a, could you put 2 plus h and put 2 here, and you would have an actual number answer instead of an a answer? Does that make sense?
Yeah.
And I'll be here throughout the day today, after school today. If you can get started on it, it'd be kind of nice. But if not, it's okay, and we'll kind of figure it out tomorrow. I just have one more example. But this is the assignment assignment sheet, Sarah.
It does say like x equals 2, can we still plug in a?
And then do it at the end? Yes, every single time. You want to just do it with a as a problem, and then at the end plug in what a is. That works. You can also just plug the number in. I might try to find a video from Patrick and I put it on My Big Canvas tonight if you want another example, maybe with a number, since we didn't quite get to that today. We're up to 8 people on Remind 101, so just another reminder, there's still 8 of you that have assignments. What's wrong? You'll be okay.